Okay, so let's unpack this. We're diving deep into a source today that sits right at, well, a really important intersection.
Yeah, two massive global challenges,
Hmm.
energy and the environment.
Definitely. And what we've got is this fascinating research paper. It's exploring a very hands-on approach,
Yeah.
generating electricity from alternative sources.
And it really zeroes in on using wind, but also, the fundamental physics of electromagnetic induction.
Right, and with some surprisingly common tech involved. That's what caught my eye.
So our mission for this deep dive, it's really to get under the hood of this, understand maybe the ingenious simplicity of how this researcher took basic physics
Yeah.
and applied it using stuff you can find pretty easily,
Yeah.
built a working prototype.
And figure out what kind of energy it actually makes and what the real-world possibilities might be, is
Yeah.
it practical.
Exactly.
And here's where it gets really interesting, I think. The source, it doesn't just talk about the gadget. It tackles some core ideas, like how we usually generate electricity with magnets and motors.
And it even takes on that whole sometimes controversial idea of free energy.
Yeah, that popular misconception. It grounds this very practical project in some pretty big ideas. Let's jump in.
Absolutely. So the paper starts by setting the scene, right? Reminding us just how critical energy and environmental issues are everywhere.
No kidding.
And as the traditional sources, fossil fuels get scarcer, this push for alternatives isn't just talk, it's becoming a necessity.
And it quickly brings us back to basics, specifically electromagnetic induction. The source points out that over 90% of the power generated globally relies on this.
Right, based on Faraday's law.
Faraday's law, yeah. The core idea is pretty simple, isn't it? Spin a conductor like a wire inside a magnetic field.
And boom, you induce a voltage. It's the absolute heart of how motors and generators work. Fundamentally the same principle, just, applied differently.
So what's fascinating then is how the paper tackles this concept. People often bring up free energy or free electricity.
And it's very clear. Energy itself isn't free. It's not magic. That's the misconception.
Right.
However, the source, the thing providing the energy, can become effectively free after you've paid for the setup.
Okay, explain that a bit more.
Well, think about solar panels or wind turbines or hydro dams. You pay for the equipment, the installation,
The initial cost, yeah.
but the sunlight, the
Yeah.
wind, the flowing water, you don't pay for those resources themselves, they just keep coming. So the energy generated is free in that sense, no ongoing fuel cost.
Gotcha. You're not paying per kilowatt hour for the sunshine itself.
Exactly. And the context for this specific research the paper mentions was actually inspired by efforts in the Philippines. They were looking into developing all sorts of renewables.
Oh, interesting. Like, well,
Compressed natural gas, geothermal, microhydro, wind, solar PV, biofuels. The whole spectrum, really. It's part of this national drive for energy independence and efficiency.
okay, so that sets the stage. Aiming for renewables like wind. But how do you make that practical? Accessible? Maybe not giant wind farms, but, smaller scale.
Right, and that seems to be the researcher's core idea. Devise a generator, using wind, using magnets, aiming to get a usable amount of electricity from something really simple, something readily available.
And this is where the surprisingly common tech part comes back in. Their key component choice. It was a brushless DC motor.
Yep. Specifically, an old PC cooling fan. You know the ones.
Wow, okay. Like the fan that stops your computer overheating?
That's the one.
Yeah.
Usually rated like 12 volts DC, maybe 0.12 amps. And they picked it because, well, they're incredibly cheap and you can find them practically everywhere.
So BLDC motors. Tell me more about those.
Right, brushless DC. They're basically modernized versions of the older brushed motors. You find them all over the place now.
Where else besides computer fans?
Oh, hard drives, CD players,
Got it.
cordless drills. Drones use them a lot. Their big plus points are reliability, no brushes to wear out.
Oh.
Plus, they're efficient for their size, good power to volume ratio, and they last a long time, like over 10,000 hours if you run them right.
And how do they work, basically?
Well, instead of brushes, they use electronics to switch the magnetic field in the stationary part, the stator. This interacts with permanent magnets on the spinning part, the rotor, and makes it turn. Simple idea, really effective. The paper mentions different designs, but the key is magnets and coils interacting.
Okay, so the actual setup here, it's almost backwards, isn't it?
Yeah.
You take something designed to use power to move air,
Yeah, the fan.
and you use it in reverse.
Uh-huh.
So when wind blows through the blades, it spins the shaft.
Right.
And instead of electricity making motion, the motion of that shaft, the rotor with its magnets spinning past the coils in the stator, that motion induces a voltage. because of Faraday's law.
You got it. The relative motion between the magnets and the coils cuts the magnetic flux, and that generates a small voltage in the output wires. It's acting as a generator. Simple as that.
That is clever.
And the intended application they showed, mounting this little device on a bicycle.
On a bike?
Yeah, or they mentioned motorcycles, even cars, to capture the wind that's created just by moving.
So you're turning your own movement, your commute maybe, into a mini power source.
That's the idea. A bit like a dynamo on older bikes, but using this PC fan tech.
Okay, but the electricity straight from that spinning fan, it can't be perfect, right? The source says you need to, like, process it.
That's right. The raw output from this kind of setup, spinning magnets past coils, is typically alternating current, AC.
AC. But phones and most small gadgets need DC, direct current.
Exactly. Think of DC as smooth, one-way flow. AC goes back and forth. So to convert the AC from the fan into the DC you need, they connected a bridge rectifier.
A rectifier, what's that do?
It uses 4 little electronic components called semiconductor diodes. Diodes are basically one-way streets for electricity. Arranged in this bridge shape, they kind of force the current to flow in only one direction. Turns AC into a basic sort of lumpy DC.
Okay, so you get DC. But the paper's results show the voltage is pretty low, especially when you're not going very fast.
Yeah, it's often quite small initially. Millivolts or maybe a volt or two at low speeds. Not enough to do much.
So there's another step needed to make it actually useful, right?
Right.
Boosting that voltage.
Precisely. And for that, they used a circuit called a joule thief.
A joule thief sounds sneaky.
Yeah, it kind of is. It's a really simple, very low-cost circuit. It's a type of voltage booster specifically good at taking a really low input voltage.
Lower than usual.
Yeah, sometimes less than a volt, maybe even less than what a standard circuit could even turn on with. And it boosts it up to a higher, more usable voltage.
How does it do that? Is it magic?
Not quite magic. It uses an inductor, a coil, and rapid switching. Basically, it quickly stores up small bits of energy from the low voltage source in the inductor's magnetic field, and then releases that energy in short bursts at a higher voltage. You trade off current for voltage, essentially.
Okay, so it takes that trickle of voltage and makes it stronger, but maybe in pulses.
Sort of, yeah. It's an oscillating circuit, so it boosts it up effectively, enough to power an LED from a nearly dead battery, or in this case, help charge something.
Right, so they put it all together. PC fan generator, rectifier for DC, joule thief for the boost. How did it actually perform? Did they test it?
They did. The source shows results from testing it, both with simulated wind, like using a bigger fan to blow on it and mount it on an actual bicycle.
Did it work?
Yeah, it confirmed the basic idea. As the bike speed increases, you get more wind, the fan spins faster, and it generates more voltage.
Wait.
The voltage straight from the fan was initially small, just as we discussed. It went up with speed kind of linearly at lower speeds, but then it curved up more steeply as they went faster.
Right, more wind force.
Yeah.
But the booster, the joule thief, what did that do?
That's where it gets practical. The tables in the source are pretty clear. It takes that small voltage and really bumps it up.
Like how much?
Well, for example, at 30 kilometers per hour, the fan alone was generating about 2.5 volts AC. But after the rectifier and the joule thief, the output was 12 volts DC.
Wow, okay. That's a big jump.
It is. And at 60 kilometers per hour, the fan made 7.2 volts AC. But the boosted output hit 15 volts DC.
15 volts. That's definitely usable for charging stuff.
Yeah. It looked like the boosted voltage kind of leveled off or plateaued around 15 volts from about 40 kilometer upwards in their tests, maybe limited by the joule thief design or the fan itself at high speeds.
But still, going from maybe 1 or 2 volts to 12 or 15 volts makes all the difference.
Absolutely. That's the key transformation. And they showed it working. There's a picture of it charging a smartphone while someone's riding the bike.
For real, that's cool.
Yeah, and they specifically mentioned how useful that could be for cyclists using GPS on their phones, which, as you know, can drain the battery pretty fast.
Oh yeah, definitely. That's a great practical example. Did they suggest other uses?
They did. Beyond phones, they listed things like powering or charging other small mobile devices, running small LEDs or bulbs.
Like for safety lights on the bike?
Exactly. That could be a great application visibility. And also charging small lithium-ion battery packs. And like we said, it's designed to be fitted onto bicycles, motorcycles, or even four-wheelers, anywhere you have movement generating wind.
Okay, so wrapping up the study itself,
Yeah.
what's the main takeaway?
Well, I think the main thing is that the researchers successfully showed it's feasible.
Hmm?
You can generate usable electricity by sort of hacking together a common motor to run as a generator.
Using wind?
Tapping into wind, yeah, an abundant source, and using other really common low-cost parts. The prototype works. It proves you can get practical power from stuff you might literally have lying around.
And this loops right back to that bigger picture, doesn't it? These kinds of small-scale, accessible projects, they add to the conversation about renewables, about green energy.
Definitely. They contribute ideas, even if small, to moving away from fossil fuels and tackling climate issues. It shows innovation doesn't always have to be huge and complex.
But they were realistic, too, right?
Yeah.
It's a prototype. It could be better.
Oh, for sure. The researcher acknowledges that. It's a starting point. There's definitely room to improve the efficiency, get more power out, make it more robust.
Did they suggest how?
Yeah.
Any specific ideas for future work?
Yep. They laid out a few clear recommendations, things like maybe try using a slightly larger motor to potentially generate more energy.
Intense.
Also, maybe swapping out that homemade Joule thief circuit for a commercially available DC to DC step-up converter. Those are often more efficient.
Okay, like an off-the-shelf part.
Right. And integrating a power bank directly into the device so you could store the energy you generate while riding and use it later, not just real-time charging.
Ah, that's a smart addition.
Yeah.
Anything else?
Let's see. Using more powerful magnets in the generator itself could boost the output, and really focusing on integrating applications, like designing it specifically to power built-in bicycle lights for safety.
Right, making it a complete system.
Yeah.
So, okay, what does this all really mean for us, for you listening? I think this deep dive, it shows something pretty surprising. That these huge principles, like electromagnetic induction, the thing driving massive power plants, can actually be scaled way down.
And applied effectively using everyday stuff. Stuff you might just overlook, like an old computer fan.
Yeah. And it puts that free energy idea in perspective, doesn't it? It's not magic. It's about smartly using resources like wind that are free once you have the gear.
Right. And we've seen a real tangible example. This prototype could literally turn your bike ride into a phone charger. How cool is that?
It really is. And it leaves you wondering, if a simple PC fan can do this with a bit of clever circuitry, what other mundane, everyday items are just sitting there?
Waiting for someone to look at them differently.
Exactly. What other abundant energy sources right around us? Maybe vibrations or small temperature differences, or I don't know, something else could be tapped into with similarly clever, accessible methods.
Yeah. What hidden potential is waiting in your own home, even?
Something to definitely think about.